Hi there, so welcome to this second video. So here we're going to work in this case. So in the deck of slides that you then load, you should have this is a problem definition, okay, the Aero 2 exercise. So let's do this problem definition. So basically this is a part, the wind design of an actual airplane, okay? So we're designing for this one. This is the Piper PA-28, very good airplane, general aviation. So let's design this wing, or let's see if this wing that we have here truly generates the required lift in cruise conditions, okay? We're designing for cruise conditions. We're only interested in the wing design. So we're not going to talk about design of the tail. I'm going to show you something, but just wing design. So here we have the required information, okay? So we have the section of the wing is this airfoil. The incidence angle, okay, so this is the structural angle. Remember, this is a fixed angle in the wing. So we have an incidence angle of 2 degrees. Okay, we have diameter angle, which for the LLT doesn't make pretty much, the LLT doesn't see this is fed, so it doesn't make any difference. Okay, and well, this is a cantilever low wing. So basically, we have here the dimension. So it's quite easy to compute the area and the aspect ratio. Okay, so it's base times height, and you have the area, and then the aspect ratio is square span divided the surface, the grass surface. Remember that in the surface we also take into account the contribution of the section of the fuselage. Okay, so we have all the information to design the wing. So the questions here are, okay, so from the POH, this is the pilot operating handbook. Okay, this is the manufacturer gives you this information. So this airplane, the maximum takeoff weight is 1,000 kilos. Okay, maximum cruise speed, you have it here, the definition. Okay, then this is the maximum operational speed at sea level, and then the stall velocity. Okay, below this one velocity will stall, and then the service ceiling is this high. So remember, you see that we can reach different velocities. Okay, also service sailing, higher altitude, different density. So everything needs to be, we need to take into account, okay, all these values to correct the lift. Okay, so higher altitude, lower density, so something we need to correct for that to get the required lift. So the questions here are, using the LLT method and ignoring the diameter angle, everything, you are asked to determine if this wing will generate the required lift to fly at an altitude of 1,000 meters and at maximum cruise speed. Okay, so here we're assuming also that we are cruise conditions, the angle of attack is 0. However, remember that we have this setting incidence angle of the wing. Okay, so this is a structural angle that we have. So before moving into XFLR5, let's go back to the Excel worksheet. So also you should have this Excel worksheet, that just to show you that is the second one, additional examples. As you open this one, you will see that here we have already the problem definition. Okay, so we put all the values here. Okay, so CL, okay, to pi, then the angle of attack, 0 lift. Okay, so this specific airfoil have this angle of attack. Okay, so you don't believe, just run Airfoil, okay, for 0 lift, and you will get this value. Okay, we have all the information, aspect ratio, area, okay, geometrical information. This in this case is easy because it's a rectangular wing, and now we just go and compute coefficients. Okay, so these are these equations. We subdivide again 4 stations, we get the coefficients, we solve for, we assemble now the matrix, we solve for the coefficients, and we get these coefficients. Always lift information is contained in the A1, so we compute it like this. So that this is our lift coefficient. Delta to compute the induced drag. Okay, we get it like this, and then the slope of this one, and now we get to answer here. So we compute everything in coefficients, non-dimensional. Now we give that a physical meaning, okay, by computing the lift. So we have the lift equation, and we say that the weight of this airplane is here 10,000 newtons, 1,000 kilos. Okay, 1,000 kilos static gravity. Okay, is the force that you want to keep. So 10,000 newtons, you put it here. So let's say that you are flying, we say 100 1,000 meters. So here you have the value already, 1,000 meters. Your density will be like this. You put it like this and see that you just solve for the equation. So at the maximum cruise velocity, so as you go into your problem formulation, it's 60 meters per second. Yes, it is generating the lift, and actually it's generating more. So remember that here we're just solving for this. In reality, when you assemble your whole, you put together your whole airplane, you add also the tail, and it's likely that this tail is going to generate a downforce just to balance the airplane, so your lift, total lift, will be lower. Okay, but see that, yes, this wing design it generate the required lift. So it's not any very fun, it's not a super fancy method, it's very simple, but it works. Okay, so there is no need to go to sophisticated methods such as CFD, stuff like that. Okay, at the beginning, at the initial step, this method, it works, it's very good. So we have the solution here, and actually here we solve for the velocity for the required lift, and actually it's telling us that, okay, instead of 60 you can go 55 and you will have that required lift. Okay, by the way, I also didn't mention here that you can compute the downwash, that is the correction or the wake. Okay, so you have all the information and you can get the downwash. So let's go and also answer the second one. At what angle of attack you will need to fly if the cruise velocity is kept constant at 55 meters per second and you climb to 2,000 meters. Okay, so let's go here, 55, and we climb to 2,000 meters. If we climb, means that density is lower, and here we have already the value. It is 1. So as you put it 1, see that you are not generating the required lift. Okay, so let's go back and let's go and let's say that, okay, let me put 4 there. So remember, it is actually 2 because we have the incidence angle. Okay, so here I didn't do that division of incidence angle plus angle of attack. So taking into account that here 2, okay, an angle of attack 2 here corresponds to 0 because we're adding the incidence angle by definition. Okay, if I go 4, this will be angle of attack of 2. Okay, so it is angle of attack minus your incidence angle is your effective one. So if we put there 4, which is equivalent to 2, see that we have here too much. So let me go to 3, which is 1 degree angle of attack. If we look at that in terms of the fuselage, okay, it means that now the fuselage is 1 degree, okay, over the horizontal line. So 4 degrees is 2 degrees, okay. So because you have that angle here at the root. So we go to 3 and see that in 3, that is, voila, we have the value 55, 10,000. And then you can answer the other question. So this one, what will you do to generate the required lift at sea level, max, cruise speed, and at an angle of attack of 0, okay? So 0 means we leave it at 2 there. So we leave it here at 2 because we have the incidence angle. So see that if we go to those conditions at sea level, this one will be 1.225. Okay, and this one is 60. So what would you need to do? You are already generating the lift. So nothing, okay, but have in mind that as you're generating more lift that the one you need, you are going to have a vertical acceleration, okay, the airplane will go up. So probably if you want to keep at level fly at the same height, you likely will need probably reduce this one, okay. So this is it. Say that very something that maybe you think is complicated, it's quite easy. We have the Excel workshop here to do that. Also, I gave you some scripts in MATLAB and Python where you can do more stations, but you can understand well what is happening using that script. So at this point, let's launch XFLR5 and see how to set up this problem. We saw that it works. That wing actually is okay. So when you launch XFLR5, okay, you're getting this wing. So I will first design the wing, okay, but also you first can load the airfoil and get the polars, but I will go for the wing. So I go here, okay, and I want a module wing and plane design. So here we don't have anything, okay, or probably we have a default airplane if we go to design. So we go into plane here, define a new plane. Okay, so it is proposing this, okay, and starting from this we can add more stuff. Okay, so if you want by plane, you add the second one. Here we don't have access to the fuselage, we need to use another method, but you can add everything here. So we don't want fin, we don't want elevator, we only want the main wing. Okay, we're interested in designing the main wing. So we go here and now you press define. So okay, here we're selecting what we want to define. So you can call this one, I know, you give it a name, PA-28 version 1. Okay, define, and now we give the geometrical characteristic. So if we go back here, see that we have everything here. So the semi-span that I need to define in XFLR5 is 4.6. So see that 0, 4.6, you have it there. Then the chord, it is 1.6 meters. So 1.6 here, 1.6 here. Then I don't have offset. Okay. So here is 4.6. Okay. And I don't have offset. Remember, this one is the one that is going to give you the sweep angle. Okay, so put it to 0. No dihedral, we don't need that one. And twist, we have a physical twist there. Okay, this is a geometrical twist. There is 2 degrees that act the root. Okay, and it's the whole wing that have that angle, that incidence angle. So the whole wing is put at 2 degrees. Fuselage always horizontal. Then we need to define the airfoil. But see that we cannot choose anything because we haven't drawn that one. But this is already the definition of our wing. So see that here we have the area and aspect ratio. So if you go back to your Excel worksheet, or you can do the computation manually, you will have area, okay, aspect ratio, and surface. See here 475, 1472. You have it there. Everything there. Area, aspect ratio, and more information. So this is the wing that we design. So see that we have also one section. But for instance, you want to design a wing with more sections. Okay, for instance, the first section you want it to be rectangular, and you want to see the second section with taper. You insert one. So I want it to after section 2, and see that there you can add the new values. So you go here and then add the new core. Probably this one will be 0.8, and then you go. So you get the idea that if you want to design an elliptical wing, you will need to add many of these sections and give the right angle until you get that. So you can add as many as you like. Okay, it's up to you. I will leave it like this. It's rectangular, no need to do that one. Maybe if I want to control the geometrical twist or add aerodynamic twist in different sections, I can add another section and control in that particular section. Okay, but there is no need to do that. Okay, we're okay here. We have our wing, but we need to give the airfoil information now. So I close here, save. See that you have your wing there with no cross section. So now we go back in module, and you go back and you go here, Airfoil direct analysis. So now we go to 2D, and we're going to get the polars of the cross section of this wing. Okay, so recall that in our problem definition we have this airfoil. Okay, so in the data that you have, you should have that airfoil as well. So if I will recall, now let me go back. Okay, here you have this folder, and then inside you have this folder, airfoils. So if you go here, see that you have your airfoil there. Okay, 65415, this one 65415. This is the one that we need to use. The format, it is exactly the same as in Xfoil. Okay, so as you recall, this is exactly the same. So to read this file, you go here. You go File, Open, look for that file. So it's airfoils, and we want to read this one. Open. Then let me go here, for instance, you go here, see that now you have your airfoil here. You load the airfoil and see that you load it with this name that is already in the file. You can also rename it. So now that you have this information, you have this physical airfoil, you can run, okay, you can run the analysis to get the polars, okay, at a given Reynolds, okay. But it's important that we need to know what is the Reynolds of the wind, okay. So let me go here to wind and plane design, okay. So see that you have all the geometrical information, and let's say that I want to run this analysis at 16 meters per second. You can compute it, okay. But if you go here, define analysis, type 1 is fixed speed. See here that you define velocity. Okay, by the way, probably you don't see this symbol here. This corresponds to alpha and beta. This is side slip. Okay, I don't know why you don't see that. Or I don't see that. So I put here 60. See, that is telling me that this wind, the Reynolds, okay, is 6.4 million. Okay, so I need now, remember that we need the information at the specific Reynolds. So we need to run for this specific value. So let me go back, okay, module, X4 data analysis, and I go here in analysis. I will do a single analysis, define an analysis, okay, and you just put your Reynolds there. Okay, by default here in this program, XFLR5, the number of iterations is 100. Here you can control the transition parameters. You want to add the correction for compressibility and everything. You have it there. So I want to run for these ones. Also, you can give it a name to that specific polar. It's up to you. I will leave it like that. Okay, you define the problem, and now you just run here. Okay, so see, you go here to your right. So we want to run a sequence. Probably you have it like this. If you want to run a sequence, select sequence, and like in Xfoil. So from -5 to 25, steps of 1, or probably steps of 0.5, and select all these boxes. Okay, you want to save everything. Analyze. And voila. We have all the angles here. So you click, you will see different values. This is the CP distribution. You go here, you have the polar, okay? So for instance, right click here, you have different options, so you can show only associated polars, and you can play around with these options, okay? What you want to see. If you want to hide, here you hide everything. If you want to change the color or symbols, you have everything there. Now styling. And also if you go into the plot, right click, and you have everything here, okay? So you can export the current airfoil, the current polar. So probably it's a little bit more friendlier than the Xfoil, but I prefer Xfoil. Change the type of the graphic, okay? Also, for instance, you go into graph, you can see just 2 graph, 4 graph, all graph. I like to put it like this, all graph. So see that this airfoil have the drag bucket, a very nice polar. We run at Reynolds 6.4. So see that here you have all information safe. Reynolds 6.4, all these angles. So let's say, for instance, that I want to run now another analysis at a Reynolds of 2 millions. You put it like this, 2 millions, you Reynolds, analyze, and off you go. You have it there. Another Reynolds. Okay, we study already airfoil, so we know what is the dependence, now what happens when we reduce the Reynolds. And here we have the results. Okay, so let me change the color here. Lower Reynolds, okay? So see that now we have, let's say in memory or buffer, we have 2 Reynolds numbers. So all this information that you have here, it is saved. When you go in 3D, automatically the software will access this, okay? So I will stop here. You get the idea. Later I will show you something else, how to run many Reynolds. So if you want to run, for instance, now 2.1, 2.2, you can define many analysis, or you can go bash analysis and see that here you can give a table of Reynolds. So you can insert everything manually. Later I'm going to show you that, okay? So we have these two Reynolds. Save the project, okay? So in your homework, I will ask you to send me this file. So you save it as, and you put it whatever, and I will call it here test1, and save it in the format, okay? And this file you need to send it to me. You can reopen, you go, and here you have, you select, and you will reopen your file, okay? So I recommend you also very often to save it, because sometimes it is a little bit unstable, so sometimes it crash. So save it very, very often. So now we go back to the 3D model when I'm playing design. Okay, I'm here, or plane, current plane, and I want to modify the wing. Okay, so we define the plan for, but I want now to modify it because I have the airfoil information. So see that you select here, we have only one airfoil. Okay, if I run for another airfoil, you will have it there. So later I'm going to show you and all of that. So see that now you put the airfoil, and this is your actual wing. And when you load this airfoil, automatically you are loading the information that you have there, the polars at that Reynolds number, all those polars, okay? So that we have that, we save, and at this point we're ready to go, okay? So we need now, okay, see here that you look at the screen, you will see that you have all the geometrical information, okay? Very important. You have the MAC, everything here, aspect ratio. So we can run an analysis. To run analysis, you go here, analysis, define analysis. So the analysis, okay, you have different tabs, okay, and you have different modes to run, okay. So you have here fixed speed. This is the one that we're going to run, because let's say that we know already this velocity. It's telling you, okay, your maximum velocity is 60 meters per second. You have your estimated Reynolds number, and you run for that one, or another velocity. But also you can run for, if you don't know that velocity, for a fixed lift. So you fix the mass of the body of your whole configuration, airplane or only the wing, and then you are going to change velocity, but also angle of attack, just to get that fixed lift. Okay, later in another case I show you that. Also you have fixed AOA, so this is this one. So you fix your angle of attack, and you will be able to change velocity, sequence of velocity. And this is size leap, more for stability. For us it's not important. So this is the one that we're going to run, okay, for most of the time, okay. Then analysis. These are the methods that you have implemented. So see that you have different methods. We're focusing LLT. And look at that, the LLT by default is viscous. You have it there, but the other methods are vortex lattice, and you have the option to enable or disable that correction, okay? So this is a correction that you can enable or disable. I recommend you to use this one, okay? Disable this option, okay? These are very, very robust methods, but all these methods are implemented, no, it's potential with no, they're full in basics. So this is something that developers of this software now implemented. It's a trivial correction, but I have to say it's not very accurate. Okay, so run it in visit. But we're interested in the LLT. Okay, so just want to enable the here sometimes. Here in inertia, for instance, you want to define the weight. Here's where you define. So this will be your target lift if you put a weight there. So we want to use the plane inertia, no, of whatever you design there. Reference dimensions, computed automatically by the software, all this stuff. Aerodynamical data, so this is just viscosity and density. Okay, so you can, this is a table that you have in the software, so you just can give the altitude and temperature, and this will be corrected. And extra data. So remember that if you run an analysis full in visit, you can add the CD0 or whatever drag. So this is just those additions to your CD total. Okay, see that here, you just keep adding. Okay, so you know those values. So for instance, you know that the fuselage produces this drag, the pylon produces this drag, the nacelle produces this drag, the aerodynamic fairing produces this drag, excrescence, that drag is this much. So you just keep adding here. Okay, it's just that. So in this case, let's run for this basic configuration. We save and see that after we define our analysis, now here, like in 2D, you can run a sequence. So see that we are interested in wing design here to design the wing for cruise conditions. Okay, that is our our condition. Okay, cruise condition. So usually cruise condition, you need to go like in the wind that we go like from minus 8 to 25. Here it's just probably -4, I think. From -4 to 10 is okay. Step plus 1 or 0.5. So let me put here 0.5 and analyze. Okay, probably this one to initialize LLT and then analyze. And this is it. Okay, so see that I launch and I get in this message. It's telling me that, okay, the flight envelope, okay, it is outside of the values that I computed. So remember that in each section we're computing the properties, okay, at this range, but then somehow the software needs to interpolate. So it's not enough to give one value. We need to give more values, okay? So you will very often see this value. Don't enter into panic. This only means that you need to add more information to cover that Reynolds, okay? And this is what I say, that it's recommended to add steps of 100,000. So 6.3 and 6.5 should be enough. So let me go back to Airfoil direct analysis. So see that I have 6.4. Let me run another analysis. And I will run it at 6.3. Okay, analyze. 6.3, we have it there. And let me run another one. Okay, analysis 6.5. Okay, so now I have enough data that it can interpolate between 6.4. So it's given that error, probably it's numerical precision, no, that it needs more data, but I think it will be enough to add this. 6.5, analyze, and you have all the data there. So see that you have all the curve. Remember that here you click the X and you can hide difference, or you can change the color. So let me put this color and then you show. So this difference is very small, so see that this curve, they overlap, okay? So it makes no difference doing that, but this software is kind of asking that now, so it's very small differences. I'll save. Let me go back to Win, okay? So now you have all that information, and it's a personalized. See that now you have a solution. It managed to interpolate, you don't have that error, okay? So see that we run from -4 to 10. Okay, so we want to see the polars are located here. Okay, so let me go to polar first and see that these are our polars. Okay, so here in graph, see that you have a few things. Those you want to 2, 3, 4. I already mentioned that. Right click here. Also, you can soon fit. I will press R, and it will adapt to the screen. No, it will scale automatically, and see what we have. Okay, for this wind. Okay, we have this. So we added the incidence angle. Okay, so see that this one is generating kind of what we wanted. Now it's a little bit here, 13,000. Okay, at 0 AOA. Okay, so from the fourth section we got it 11,000 if I well recall. Okay, so there is some different, but see that it works very fine. So for instance, if this is too much, just reduce the velocity, or actually the problem was also density. If we recall, it was 1,000 meters, okay? So 1,000 meters density is 1.1. So let's redefine the problem. Define analysis, aerodata, and it's from altitude, okay? So it's 1,000 meters. And here you have your density and corrected viscosity. Save. Okay, we want to save it with the same name, or overwrite. And let me rerun. And voila. See that now with that correction, see that it is lower, density have a strong influence, and we're there. Okay, so this is all your aero data. You have it here. Then as you move here, this one, you can see for each angle, you can see this is the, in this case, this is the induced angle. So let me go to 0 degrees. I press R, okay, fix to screen, and see that from the mid section to the tips. Okay, see that this is the downwash. Okay, so this is the angle now that it will create that thick vortex. So see that at the strings is very, very, very large. So there's where you have all the vortex. Here also now again graph, you can use 2, 4, all graph. I like to use 1. So see here that you have 1, 2, 3, 4, 6 keys. You just press 2. 1 is induced drag. 2 is total angle. 3 is CL. So let me go here. I press R. So this is the span-wise lift distribution. So it's called from the lectures that this is the one that follows now. Then 4 is the total lift. Okay, let me press. So this is your actual lift force in each section. So remember that you will need to integrate this one to get the other lift. But this is the one that you have there. And see that this curve there in gray. Let me change the color of this one also. Color and put it like this. This represents the ideal lift distribution. Probably you don't see this one by default. You need to enable this one. Right click and you have it here. Show target curve. And you can enable or disable. See, disable, show target curve, and show elective lift distribution. Okay, so this is the ideal one. I want to use the max local CL. Okay, be careful. And this is it. So our idea when designing the wing, we already know, let me go back here, that we're producing the required lift. There is no problem. Okay, there is no deal there. The problem now is that we want to do things in an efficient way. We want to reduce the induced drag component, and to reduce that one we need to get closer to this elliptical lift distribution. So now what we can do is just play a little bit with the geometry to adjust that. So you have access to your geometry. You can start to change. I know you can add washout to control here, or you can add another section here to control a little bit more here. Okay, so it's up to you, but this is the idea. First, be sure that you generate the lift at your desired conditions, okay? Then adjust your distribution to have the elliptical one, but always check that you still are generating the required lift. Other things that you should be careful. I'll always talk about this moment. For the moment, you should be very careful, or for you it's important that the airfoil that you choose is an airfoil that does not generate too much moment, okay? Because then to balance this configuration, the airplane, we need to add a tail, okay? And the tail will, in this case, generate downforce, so that also will, you will reduce the total lift. So you don't want to use a configuration that have too much negative moment that will require a lot of downforce to balance. And also it is ideal, but it's something that is also difficult to achieve, that your maximum LD, it is the same as your cruise angle. So let's say that our target cruise angle is 0. It is ideal that the maximum LD is also at 0. Okay, for performance reasons, but it can be tricky to get. But there are some designs that you can get it, or you play around with the twist and everything. You will see that you will manage to twist it a little bit, to shift it a little bit to the right, and you can put it even closer now to the design condition. But let's say that in our case, our target is 10,000 newtons. So see that by looking at this curve, we need to be about -1. And actually the maximum LD, we're very close. So this is an optimal condition. Probably I don't like that we're at -1. Okay, but if we manage to shift it to 1, it will be better. Okay, so you go angle of attack of 0, which is the optimal one that we should aim. But this is already a good design. So also try to keep your cruise angle something between -2 and 2. Okay, that is a good value. So this is it. This is how we get it. So now that we have this curve, as always, you want to right click. Remember, right click. You can save this screenshot. You can export this data. Okay, you have the current polar, for instance, and I think export results. Okay, and you save that data in text format. So let me show you here. Current polar, export results, and I put it in the desktop and I have it here open, and see that you have your data there. Okay, so you see that for each angle you have CL, induced, viscous, CD. These components are not computing moment. You have everything here. Okay. So let me go back here. So now we look at here. We look at here also. You can get from this one so different. See that different angles, you have different distributions. Okay. Then probably here, I know you have the animation. Okay. So it's up to you there. Okay. And the other one that I want to show you, this is for stability. We don't need to do anything here. And this is also to show you CP. Also, we don't need to do anything there. We go in this one and we can see the whole airplane configuration. Okay. So see that we have the option here also to visualize some information. So see that you can see lift. This is just something visual. Okay. Some people likes to have this visual reference. Okay. For us, it's more than enough this. Okay. But here you can have those vectors. And for instance, induced drag, and you have here also this one is telling you where you are producing more induced drag. Okay, so kind of this is it's not a data indication, or you don't have any scale to know how much you are producing here. To know that one, you should come here and plot out those distributions. Okay. So you have induced drag. Also, for instance, you can know your moment. This is pitch down or pitch up. So in this case, you will see this rotating pitch down. You can have the viscous drag also. You can visualize that one. Remember, it's a non-linear method. So see that you have also that one. And see that, as I say, that the induced drag is a very large component. See that is almost as large as the viscous drag. Okay, but however, as a designer, we can directly add on the induced drag. We can reduce it. Okay. Instead, the viscous drag is very difficult. It's related to the surface. Now, so the only thing that we can do there is choosing a laminar, natural laminar flow airfoil, and designing a very clean wing with no interference, nothing to reduce that one. But that is difficult to control. Instead, the induced drag, it can be controlled, okay, by using good designing practices that we address in the review. So this is just to visualize those vectors. Okay, it's not that important. For us, it's much important. You can leave it on. For us, it's much important these distributions. Okay. So now that we have this airplane here, let's do another one. Okay, but another one with a different airfoil. Okay, so we have this one, and let me say that I want to duplicate this one. So see that I go here. This is the whole airplane or the wing. Duplicate, and I will call it V2 version 2. Okay, I duplicate it. I don't want to redo all the design. Okay, and now let me go back. So there you are going to have all the definition already. So you have, okay, I can hide that one. Let me go back to direct analysis, and let me choose another airfoil. So if I go here into design, see that in design you have NACA foils. So this is like an airfoil 4 or 5 digits. So let me choose a 2412, 100 panels, and there you go. Oops, I think it's going to crash and make here. Yeah. So as I say, very often you need to save it. Okay. And let me go here, let me launch again. So I save it, but I didn't save the latest one. Okay, so probably, okay, analyze. Okay, I have a solution. Let me save. Let me go module and analysis and not airfoil, and let me choose an airfoil here, 2412. Okay, now I have it. So see that sometimes mysteriously crash. I don't know why. So see that this is the 6-digit and the new one. So see that they are different. So let's see what happens with this new one. So as we did for this one, let me save it. We need to run for this Reynolds number. So I go analysis. But now let me show you the batch analysis. Okay, you can do it manually, or batch analysis, you have this table. So in this table you go, let me go 6 million 6.661, and you just fill in this table. Unfortunately, you need to fill it manually. It's not like you put what the extremes and then it's going to add the values in the middle. You need to do this manually. Okay, this is the only thing that I don't like, but it's not a problem. Put it here, then 6.4, and let me go up to 6.5. Okay, and then this one I can erase. So if you want to erase, you click there and delete, or if you want to add a new one, you have there the options, and it will add. Okay, so I delete everything. I have here 6 design points, Reynolds 6 million. Also, if you want to add the Mach number, you can add it here for the compressibility correction. Here you have the transition points. So that's all. You define your batch analysis, select your airfoil. So be careful that I want just to run for this one. See that also you can run in parallel as you have different. So in my case, I'm using 6 cores. Okay, there is no problem. Define your angle of attack from minimum of -5, maximum 25, these steps. So basically what it's doing is that for each Reynolds, it's running all these angles. So Reynolds, run out this angle. Reynolds, run out this angle. Also, as we're running in parallel, we'll launch everything at the same time. So, well, they're already fast computations, so we don't want to makes no sense now running faster, but that's all. You could have done the same manually. Okay, define analysis, run one at this, and that's all. Okay, so this is just to make it easier. Here in advanced setting, you can access this stuff for 100 iterations you want, or you change that one. Okay, so let me run and see that very fast. We have everything. Okay, and so you go here, see that you have all your Reynolds. Okay, automatically save, and now you have the airfoil data, and you can use it. So if I go back to wing and plane design, okay, now let me duplicate this airplane. Okay, let me go here. Probably it crashed previously because of that. Let me see. Duplicate. I want to call it B2. Okay, we have the duplicate. I save it. And now plane, I want to modify the wing because I want to use the new information. So see that now I have this. So new airfoil, or we can add the aerodynamic twist. Okay, so but I want just this, my design with a new cross section. Let's see what happens. So the performance of this airfoil is not as good as the CD6, or we think. Let's see what happens. We save, go here, analysis, define analysis, the same. This is the velocity. We are sure that we're covering the Reynolds numbers. Analysis, nothing else. We have the here. Okay, let me define at the right altitude. Okay, right value, save, and at this point, ready to go. Analyze and see that the new airfoil, actually the performance is much worse. Okay, well, not much worse. Okay, but probably will be better in terms if I want to have. Okay, so if I want to have my cruise condition at 0, it is better. But if I want to have a larger angle here, no, when in CL0, it's better to use the other airfoil. Okay, but see that different airfoils, we get the same behavior, and see that in this case is the decided behavior. No, 0 angle here. The LD corresponds to the maximum. This is ideal. This is what we want. So let me make the difference here. Also, let me change the color. See that the new one, okay. Also, it produces more drag. Okay. So here the big difference in induced drag. Okay. I think okay, viscous also, because this one is laminar, and see that for large production of lift, large angle of attack produce less drag. So remember, you can always come here, define graph, And for instance, let me see the viscous component. Okay, let's see the difference. And see that clearly you see that this one, here you have your drag bucket, okay? Instead, the other one doesn't have it. And you can go, for instance, define graph settings and the induced drag. Okay, I choose the wrong axis, but okay, let me change. Let me put it right. So define graph should be CL induce here. Okay. So it's difficult to see, but maybe, yeah, it's difficult to see since that they're almost all overlap. Okay. Actually, yeah, they should. Okay, so this is how we proceed. Okay, so again, you can come back here and you can get access. You click there, and then you have the angles. Okay, remember that you expand and you go to 0, as you want to see all your arrows and this stuff. So this is mainly, see that also this is represent the transition, when the transition happens, okay? And you have access to that information because you are running Airfoil in viscous mode, and you have all the transition location. So important things that also I want to point out. So recall that you have all the coefficients, everything, but there is another value that is very important and a good indication of the, if you have a good wind for the optimal lift distribution. As you look at here, okay, you have this number here, efficiency. Okay, so this is the wind efficiency. So this is that coefficient that if it is 1, corresponds to the perfect elliptical contribution. Okay, so you want to have this as close as possible to 1. However, be careful that this is a nonlinear method, iterative methods, okay, with some corrections. Sometimes it might happen that it gets greater than 1. That doesn't mean that it's a super wind. It's just something numerical, okay? But if it gets greater than 1, it means that is close to 1, okay? But it might happen, okay? But our goal also is you want to check a value to see the efficiency of the wind, okay? How close you are to that elliptical contribution. Just look at this coefficient, okay? So if I go here now, let me select 0, see that, and let me go to local lift, okay? This one, okay? So this is the version 2, it's the NACA the NACA 4 digits, and we look at the other one, okay? So see that the lift distributions are the same, there is not large difference there, okay? Or probably, let me see, there is something that it shouldn't be, okay? Boom, boom, boom. For instance, let me check 1, okay, induced drag. And induced drag, okay, this one there is a slight difference there, so there are small differences. Okay, so total angle so if I look CL for this is the CD6 and CL for the other one, so there are some slight differences, okay, well there are there, okay. So you can compare your winds, your distributions, and so on, okay? So this is how we proceed. So let me do something else just to show you, okay? Let me save, okay? And we can, the last modification, let me create a new analysis here, duplicate, version 3. So in the version 3, what I want to do, I go plane again, and let me modify a little bit the geometry. So see that we have this twist or this settling angle, okay? I don't want to put that angle, okay? So let's see what happens now. So you define there, let me save. We don't need to do anything because this is the Reynolds, so define your analysis, everything okay here, Aerodata okay, analyze, and there you go. We have the new value. Let me change the color. Okay, and see that settling angle that we added, the fixed geometrical angle, have a strong influence. So now see that to arrive to that condition of 10,000 newtons, you need to fly at an actual angle of attack of 2. Okay, previously we were at 0, but remember that we have that geometrical angle. Okay, so it is also important in terms of comfort of the passengers. Now you have the fuselage, you want it to be as close as possible to 0. Maybe 2 makes not much difference, but our goal is always to get as close as possible to 0. Ideally, remember also that you want to have your cruise condition also where you have the maximum CL, the LD ratio. So see here that this is also the case. And also see that this is the trim. Okay, trim is very important. So the trim, when you intersect this line here, the 0 moment line, means that the aircraft is in trim conditions. To have the perfect trim condition, you need to be here at the same cross angle or something around the cruise angle. In this case, to trim the airplane to be in exact equilibrium, you need to go something about -5. Okay, so this is not balanced, but it's just the wing. Okay, so when we add the tail that I'm going to show you next video, you see that everything starts to balance. Okay, so this is the case that here, no settling angle, and now let me do another one. Let me duplicate with twist. Okay, geometrical twist, and probably we can add also aerodynamic twist. Okay, so I go here, save, plane, modify the wing. So let's say that I wanted to route this airfoil, and I want to add a small twist. I want to go from from 2 to 1. Okay, so at the root is 2, and here is 1. Always I have my angle of attack in reference to the flight path. Okay, this is a physical angle, remember. So I define that one, and let's run this new wing. This is okay. Save every now and then, analyze, and probably we don't see a difference. Let me choose symbols, this one, and new color here. And there we go. So see that now by adding, so the gray one was the first one with the City 6 only. This one, now we have the aerodynamic twist, but also geometric twist. Okay, so see that is good behavior. Okay, now this one is trained at 10,000, what we wanted. Okay, and see that also good properties here, and here also close, very close to 0 condition. Okay, so see that small modification, okay, was enough to go to that design condition. But what is important that also we need to check here. So if I go to 0, let me go, and now this is radically different, like we have seen. So see, by adding the twist, geometric and aerodynamic, see that now we're much closer to that ideal elliptical lift distribution. Okay, so let me go back to this case. So see that in this case, see here that we have this problem here. This is a problem you are producing here. This is a excess of lift, okay, that you're producing, and this is responsible. This excess here is responsible for the large induced drag. Instead, in this case, much lower. Okay, here maybe we have a problem, but it's much better than the previous one. So this is already an optimal wing, this one that we have. We are producing the required lift, and the minimum here we have the lower induced drag, very close to the elliptical lift distribution. So for instance, what we can do here in this case, here in this section that is not close to that one, maybe we can add another section here. You can say at 2, you can add another section and add a little bit more of twist to go closer. So let me show you that. Okay, so see that it's not that difficult. Let me go also back here, and again you can see everything. Now in this case you select your angles, but see that in 0 our efficiency, see that is 1. Okay, so it's actually larger than 1. Remember that there are numerical problems here, but you already see that it's much better than all the other cases that it was 0.97 whatever. In this one we're getting closer. So this is our goal. Okay, so let's do the final modification. So let me duplicate this one. I call it 5. Save. I go to plane, define new plane, sorry, not new plane, modify. Okay, so already exists, so I don't need to create a new one. And what I want to do is add a new section. Okay, I want to have more control. So let me No. Click here, insert here, and see that insert, I have this section here. We say that we want it at 2, that section, okay? And see that now that you have that section, you can control twist. So for instance, look at that, if I put 6, you're doing that, okay? So here you go from 2 to 6. So probably it's not very nice. Okay, so let's put 1.5 and I will leave this profile there. So see that I'm using this series 6 in all this section here, and then in the outer section you are doing the aerodynamic twist plus that geometrical twist. So let's see if this modification has an influence. Okay, so we define the analysis, save, and we analyze. We have our plot there. We check the polar. Okay, we have the polar. So let me hide here. When you deselect that X, you're hiding all the others. So I want to have these two, okay, the last two, and see that actually the new one, it is an improvement of the previous one. So we added the new profile. See that we get better. Likely, probably we're going to improve a little bit this distribution. And voila, see that? Much better. Okay, so we go, let me go here. Previous one, which is already better than B1, B2, B3. Now we go to B5, B4, and look at B5. Very close to that one, okay? So this is, at this point, this is, probably you can do better. You can add more sections. So see that you have to, probably here you see that at 4, maybe you don't like this one, so you can control a little bit more there. Okay, you can be a little bit more punctual there and control, but this is already a very good distribution. And see here that your efficiency is 1. So at this point you can stop. So see that we designed this wing, okay, and now we improvement. So probably you can say to manufacturers, the Cherokee, now the Piper Corporation, that this is not a good one. You can add some better twists to get something much better, but they have their reasons to have that wing that already works. So this is it. This is how we design our wing. Always remember to save here, and then, well, you can do all the post-processing that you want. Remember that always right-click here. You have many options, so I invite you to play around with these options. So if you want to see the log file of your simulation, you have it there. So see that everything converges. So probably sometimes you will have that error that is outside the envelope, meaning that you are missing a Reynolds, so you need to go back to 2D and run get more Reynolds numbers. Okay, so this is it. We're here, okay, and okay, I hope you got an idea how to use. As you see, it's not that difficult, okay? So play a little bit, control. In this case, we use this rectangular wing, which is not the ideal. So in later videos, I will show you the taper ratio and everything that we can control even better. Okay, so like the Sibyl's wing. So that's all for this video. In the next one, I will show you adding detail. Okay, so we have the case here, add detail, but we're going to address a little bit more stability. Okay, not very related to aerodynamic design. So thank you for your attention. See you next video. Bye.